Welcome to this presentation on finding the longest subarray with an equal number of zeros and ones and how we can solve it efficiently using hash maps. Let's dive into the problem and understand how we can approach it step by step. We are given an array consisting of zeros and ones. The goal is to find the length of the longest contiguous subarray in which the number of zeros is equal to the number of ones. For example, if the array is 1 0 1 1 1 0 0, the output would be 6, as the subarray 1 0 1 1 1 0 has 3 zeros and 3 ones. In this example, the input array is 1 0 1 1 1 0 0. By carefully selecting a subarray, we can find that the longest subarray with equal zeros and ones is of length 6. There are also constraints to consider, such as the size of the array, which can go up to 1 lakh elements. Our solution needs to be efficient enough to handle such large inputs. To solve this problem efficiently, we use a technique called the prefix sum. But here's the trick: we treat zeros as minus ones. This transformation helps simplify the problem, as we can now focus on finding subarrays where the sum is 0. We will also use a hash map to track the first occurrence of each prefix sum, which will help us identify the largest balanced subarrays. Let's go through the algorithm. First, we initialize an empty hash map to store the prefix sums. Then, as we traverse the array, we update the prefix sum by treating zeros as minus ones. For each prefix sum we have seen it before, we calculate the length of the subarray from the previous occurrence of this sum. If not, we store the prefix sum and its index in the hash map. By keeping track of the maximum length of subarrays found, we can get our final result. Here's the implementation in C++. We initialize the hash map with the first prefix sum, which is 0 at index minus 1. Then we loop through the array, calculating the prefix sum at each step. If we encounter the same prefix sum again, we update the maximum subarray length. Otherwise, we store the new prefix sum with its index. This approach ensures that we only traverse the array once, making the solution highly efficient. Let's walk through the example. We have the array 1 0 1 1 1 0 0. First, we convert the zeros to minus ones. So the array becomes 1 minus 1 1 1 1 minus 1 minus 1. Then we calculate the prefix sum 1 0 1 2 3 2 1. As we process each element, we use the hash map to find the first occurrences of each prefix sum. The largest subarray with equal zeros and ones is between indices 1 and 6, giving us a length of 6. Now let's discuss the efficiency of the algorithm. The time complexity is big of n, where n is the size of the input array. This is because we traverse the array once. The space complexity is also big of n due to the hash map used to store the prefix sums. This solution scales well even for large input sizes up to 1 lakh elements. To summarize, we used prefix sums and hash maps to solve this problem efficiently. By treating zeros as minus 1, we were able to simplify the problem of finding balanced subarrays. This approach ensures that we can find the longest subarray with zeros and ones in linear time. making it optimal for large datasets. We have covered the core concepts and solution, but now I would like to open the floor for questions and discussion. As there are any points that need further clarification, or perhaps ideas on how we could extend or optimize this solution further. Thank you for your attention throughout this presentation. I hope you found the solution to this problem insightful. Feel free to reach out if you have any further questions or need assistance. I look forward for connecting with you soon. Hello everyone and welcome to this presentation on problem bitwise OR of all pairings. In this session, I will walk you through the solution approach, algorithm and code implementation in C++. Let's get started. To begin, let's understand the problem. The input consists of two integer arrays nums1 and nums2. Our task is to compute the XOR of all pairings between elements of these arrays. A pairing involves taking an element from nums1 and another from nums2 and calculating their bitwise XOR. The goal is to find the cumulative XOR of all such pairings. Next, let's focus on optimizing the solution. Instead of brute forcing through all pairings, we use the properties of XOR. XOR is both commutative and associative, meaning the order of operation doesn't matter. This allows us to simplify the problem by pre-computing the XOR for each array separately. These pre-computed results, XOR1 and XOR2, represents the XOR of all elements in nums1 and nums2 respectively. The next insight involves leveraging the lengths of the arrays. If the size of nums1 is odd, each element in nums2 contributes to the final result. Similarly, if the size of nums2 is odd, each element in nums1 contributes. This observation drastically reduces unnecessary computations. Ultimately, we combine contributions from XOR1 and XOR2 based on these conditions to obtain the final result. Let's break down the algorithm into simple steps. First, we initialize two variables XOR1 and XOR2 to 0. Then we calculate the XOR for all elements in nums1 and store it in XOR1. We do the same for nums2 and store it in XOR2. We check the sizes of both arrays. If size of nums1 is odd, include XOR2 in the result. If the size of nums2 is odd, include XOR1 in the result. Finally, return the computed XOR as the result. Here's the C++ implementation of the solution. The XOR all nums function begins by initializing XOR1 and XOR2. We iterate through nums1 to calculate XOR1 and through nums2 to calculate XOR2. Depending on the sizes of the arrays, we conditionally include XOR1 and XOR2 in the final result. This efficient solution avoids brute force computation of all pairings and works in linear time. Now let's analyze the complexity of this solution. The time complexity is big O of n plus m, where n is the size of nums1 and m is the size of nums2. This is because we iterate through each array once. The space complexity is big O of 1, as the algorithm uses a constant amount of memory irrespective of the input size. Let's walk through an example. Suppose nums1 is 2, 1, 3 and nums2 is 10, 4, 5, 6. First, we compute XOR1 as 2 XOR 1 XOR 3, which equals 0. Then compute XOR2 as 10 XOR 4 XOR 5 XOR 6, which equals 3. Since the size of nums1 is odd, we include XOR2 in the result. However, the size of nums2 is even, so XOR1 is not included. The final result is 0 XOR3, which equals 3. In conclusion, this problem highlights how we can optimize computations using the properties of XOR and array sizes. Instead of brute forcing through all pairings, we take advantage of mathematical properties to achieve an efficient solution. This approach ensures a faster runtime and minimal memory usage. That's all for the explanation. If you have any questions about the solution, the algorithm, or the code implementation, feel free to ask.